And welcome again to our video lecture supplement series here at Troy University. And I am your usual host, Dr. Sanders. Today, what I wanted to talk a little bit about is a little demo that I do in class sometimes, and that you've probably seen, and in fact, which I tried to videotape elsewhere. And in this demo, I have a pair of rubber balls, a big one and a small one. So the big one's a lot more massive than the small one. And I drop the two of them onto the ground, and then basically one of them bounces very high. If you just drop the little ball straight down from any height, it bounces up to some height. In fact, from dropping it from here, it's only bouncing maybe about to maybe stomach level on me, for what that's worth. Maybe about a little over a meter. But if you combine the two, so that you drop it with the little one on top of the big one, then you can see that the little ball bounces a lot higher than otherwise would happen. So I'm actually going to drop them from a little bit lower, just because I don't want to destroy the ceiling too badly. Even from this height here, this little thing is going to go through the roof, so I'm going to drop from pretty low. And let's drop. Hopefully you saw the ball kind of fly up in front of me. I basically want to go over an explanation of why it does that. And so I've drawn a couple of diagrams to help me out with that. So I want to start with my first diagram, which is just considering what happens when you have a single ball that I'm going to label ball number 1. So this is just a single ball with mass M1. And from the ground's perspective, this little line with the daggered lines on it is going to represent the ground here. From the ground's perspective, right at the time that it impacts, this ball has some initial velocity, which is downwards towards the ground, and I'm going to call that initial velocity V initial. And it hits the ground and deflects off the ground. If it's a perfectly elastic collision, all that happens in this interaction is it hits the ground and reflects with the same velocity as what it had, the same speed as what it had initially, but in the opposite direction. So V final is just negative of V initial. And if you wanted to switch it around and look at things from the perspective of the ball itself, basically, initially, the ground is going to look like it's rushing up towards the ball with some initial speed. And that initial speed that the ground is rushing up towards the ball with is going to happen to be the same speed as what the ball is actually falling towards the ground with from the ground's perspective. So the ground initial would be straight up like that. Then when the ball hits the ground and deflects in the ball's new reference frame, the ground is now falling away from it with some velocity. And that new velocity that it's falling away from it with is just going to be the opposite of the old velocity that the ground was originally looking like it was rushing towards the ball with. So I guess imagine yourself as like a tiny person or a camera or something on this ball falling towards the ground, or imagine yourself in a plane crash. The ground looks like it's rushing up to meet you, even though from the perspective of most people on the ground, you look like you're falling towards the ground. So I want to take these concepts and apply them over here to this more complicated setup. So I again have a ground. I have a larger ball, which I'm going to call ball number 2, and I've got the smaller ball, which I'm going to still call ball number 1. And ball number 2 has a much larger mass than ball number 1 does. So what that effectively does is I take it for granted that the ground is a lot more massive than either ball. And so basically the fact that the second ball is a lot more massive than the first means that any collision between the two should behave the same for the smaller ball as a collision with the ground would behave. So what do we have initially? Well, initially these guys both have the same downward velocity. I'm going to call it, again, V initial. And it's the same for both balls. And this black one, this black line is going to represent what the ground would see, or what an observer standing on the ground would see. So what does an observer standing on ball number 1 see happening? Well, in that case, the ground looks like it's rushing up to meet ball number 1 or ball number 2 with the same initial speed as what ball number 1 would have towards an observer on the ground. And this one and this one, both balls are basically stationary within this guy's reference frame. And the same is true from the reference frame of ball number 2. It just looks like the ground is rising up to meet both of them. And this looks like 0, this looks like 0. Okay, well, eventually the two collide with the ground, and in fact I drew this very specifically with the second ball on the ground for a reason, because what we care about is the speed right before impact. So these things hit the ground, and what happens? Well, from the perspective of the ground, ball 2 has hit the ground, ball 1 hasn't impacted yet, and so what ends up happening is that ball 1 bounces off of the ground. So ball 1 now looks like it's going upward with a speed of the initial. And ball 2 still looks like it's going downward at a speed of the initial. So now they would look like they're going to collide with each other. In this perspective of ball number 2, the ground now looks like it is falling away. I'm going to call this V after impact. So I'm going to call it V sub A for after impact. And V sub A is just basically negative of V initial. Okay, and similarly, the ball number 1, which originally looked like it had 0 velocity initially, now looks like it's rushing towards ball 2 with a velocity that's equal to this minus this. This minus this. Either way, it's going to be a speed of 2 vi. So this one now has a speed of v after impact for number 1 of 2 vi. And similarly, in the perspective of ball number 1, now instead of this one having 0 speed, this one now looks like it's rushing up to meet ball number 1 with a speed of 2 vi. Okay, now scene 3, or act 3, if you will. ball 1 and ball 2 collide with each other and ball 1 bounces off of ball 2. Well, ball 2 is a lot bigger than ball 1, so ball 1's bouncing off of ball 2 should be similar to ball 1's bouncing off the ground. So what does that look like? Well, remember that we have a 2vi here and a 2vi here. So from the perspective of ball number 2, what's going to happen after this second impact, so I'm going to call this V final. From the perspective of ball number 2 is still at rest, and this thing has now turned around and picked up one times the after impact thing, which you'll recall is 2vi. And if we wanted to also look at what ball number 1 now looks like it's doing, it would now look from, assuming ball 2 now looks like it's doing from ball 1's perspective, it now would be falling away with a final speed of same v after impact, which is 2vi. Okay, but what we really care about here is not what do these two look like they're doing in the new frame of each other, but rather what do they look like they're doing from the perspective of the ground. So, this one stays the same. V final is still roughly 1 times the initial speed, just in the opposite direction, for ball number 2. Ball number 1, however, what we have to do for it is add these two vectors together to get what ball 1's speed is going to look like from the perspective of the ground. So from the perspective of the ground, ball number 1 has 2vi plus another vi. So v final is going to look like 3 v initial. Okay, and similarly, if you wanted to know what the ground looks like it's doing from ball 1's perspective, it'll look like it's falling away with 3 times the initial speed. Okay, so that's what happens to the speeds during all of this. How does that tell us anything about how high the thing goes? Well, at this point, you now would use conservation of energy, and the conservation of energy thing basically says that the final energy has to be equal to the initial energy. And so basically the amount of gravitational potential energy gained has to be equal to the amount of kinetic energy lost. So what that looks like is 1/2 mv, whatever the initial speed is, squared is going to be equal to mgh final, whatever the final height is. So the final height can be determined in terms of whatever the initial speed after bouncing was. So that's going to look like v after bouncing, which in here we labeled v final, but here is going to now be v initial, divided by 2g. And in the case where we just had a single ball and it hit the ground, it deflected upward with vi. So h final for one ball is going to look like vi squared over 2g. In the case where we had 2 balls, this thing deflects upward with 3v. So h final for 2 balls is equal to v initial times 3 quantity squared over 2g, which is going to give you 9 vi squared over 2g, which is 9 times the height of the single ball. So that means that the second ball, if all these collisions are elastic, should bounce 9 times as high as it would have just being dropped on the ground.